We've been talking about center of mass calculations, and mostly we've been dealing with uniform or variable density rods, metal rods lately, and we want to kick it up a notch. We're going to go to another dimension. So we're going to be looking at very thin metal plates now. So we have this very thin metal plate, and it's defined as the region underneath y is equal to 4 minus x squared, bounded by x is equal to 1 and the x-axis. So that's our very thin metal plate in blue. And we also are told that this plate here has a variable density, and that's defined by this function up here. And this symbol is lowercase sigma, and we're told that it's varying in this x direction. So we have that, and then we want to find the center of mass, so the x and the y coordinate for our center of mass. So why don't you pause the video and give this a try on your own? All right. Assuming that you've given it a go, we're probably just going to get to the x coordinate in this video. So let's look at the x coordinate of our center of mass. So that's x bar, and that's equal to the definite integral from a to b of x dm, and then over definite integral from a to b of dm. Now, really, we need to talk about dm, and in order to do that, we've seen we need to talk about density. So over here, let's talk about density for a little bit. Again, this is lowercase sigma, and it represents area mass density. So it's density, but we have these units here. So it's defined as mass over area. Mass over area. Okay? And what we are going to do, again, we want to talk about the infinitesimals of these. So this is going to be sigma is equal to dm over dA. And then solving for dm, we're going to get this tiny chunk of mass is equal to our density times a tiny chunk of area. So now we solve for dm, and now let's put this back in and see what we get. So we can talk about these a little more. So we have x, and now we said that dm is equal to sigma times dA. All right, and then we're going to be dividing by definite integral of, and we have sigma times dA down here as well. And maybe I can keep these as constants right now. That's fine. All right. So we have this, and really we already know what sigma is. We're told it's 2x, so it's varying in the x direction. But the last piece here is just dA, and a tiny chunk of area, summing up all of these tiny chunks of area. And really, we already know how to do this. If I were to strip away any sort of notion of taking a center of mass calculation, I would just ask you, okay, find the area under this curve here, find the area of this region. You say, no problem, I can do that. And you even have two methods. You could slice this up with vertical slices, or you could do it horizontally. And really, we need to figure out how we want to calculate the area under this region here. And that decision is really going to be made by our density function. Because what is this density function saying? It's saying when we look at an x value, all along this x value here in this strip that we're going to take, we're going to have the same density across that strip. So we're going to take advantage of that fact, and in order to calculate the area under this curve here, we are going to be integrating with respect to x, all right? So filling that in, once we made that decision, and again, it's not really made by us, it's made by our density function. So we're now going to have this definite integral. We'll throw limits on at the end. So it's now going to be x times sigma, which we said is 2x, and then again, dA. So we're going to be taking these, we're going to take the height of our rectangles, our tiny little rectangles that we're going to add up. Height of those rectangles are 4 minus x squared. And then times the width of those rectangles, which is an infinitesimal piece of in the x direction. So times dx. And then we're going to be dividing by the definite integral of sigma times our dA. So just we're going to have 2x. We get that in orange. So this is going to be 2x. And then again, it's going to be times 4 minus x squared dx. And then lastly, let's throw in our limits of integration. So if we're integrating with respect to x, we're going to be going from 1 to 2. So 1 to 2. And this is our integral setup, and all we need to do now is evaluate it. So if you want to, please pause the video and try to get some practice evaluating some integrals. All right, let's start doing these. Let's see what we get. So I'm going to just write this up here. This is going to be 2x squared, and then we'll distribute. So we're going to have the definite integral from 1 to 2 of, this is going to be 8x squared, and then minus 2x to the 4th power, and we're integrating with respect to x. And then in our denominator, we have the definite integral from 1 to 2, and this is going to be 8x minus 2x to the 3rd power, and then integrating with respect to x. Now let's anti-differentiate and evaluate. So we're going to get what? We're going to get, in this numerator here, we're going to have 8/3 x cubed, and then minus 2/5 x to the 5th, and then we're going to evaluate this at 1 and 2. All right, and then in our denominator here, we're going to have a 4x squared minus, looks like 1/2 x to the 4th power, evaluating at 1 and 2. And let's see what we get. All right, here we go. So 2 cubed, that's going to be 8, so that's 64/3. And then 2 to the 5th, that is 32, so minus 64/5, minus 64 fifths. And then evaluating this at 1, it's going to be minus, we have this quantity 8/3 minus 2/5, minus 2/5. And then in our denominator, we have what? We have 2 squared, so that's 4, so that's 16. And then this is going to be minus 8. And then we have minus, let's see, 4. So this is minus 4, and then minus 1/2. Okay, so what do we get here? Let's get some more space. Looks like in our numerator, we're going to end up with a common denominator of 15. But maybe we can add some like terms first. So 64 minus 8, that is 56. So that's 56/3. And then we're going to have, let's see here, negative 64 plus 2. So minus 64 plus 2, so that's negative 62. That's negative 62. Yeah, so minus 62/5. Okay, so that's our numerator. And then denominator, what do we have? We have 8 minus 4, so that's 4, and then plus 1/2, so that's 4.5, so that's 9/2. All right. Now we can get this common denominator of 15, and let's see how good our mental math is. So this is going to be times, we're going to have a common denominator of 15, and then 56 times 5, that's 250 plus 30, so that's 280. All right. And then times 3, 62 times 3, that's 180 plus 6, so that's 186, so minus 186. And we'll subtract that in a little bit. So this is over 9/2. And what do we get here? 280 over 186, I mean 280 minus 186, that is 94. 94? Yes, 94. So that's 94/15. Okay. And then we flip this fraction, and we're going to be multiplying by 2/9. I'm kind of running out of space. Let me move this over here. All right, so 94 times 2 is what? Is 188. And then 15 times 9, so that's 150 minus 15, so that's 135. Oh, wow, look at that. A perfectly, a very nice number to work with here. Wow, 188 over 135. So 188 1/35 is our x-coordinate of our center of mass. There we go. 188 1/35 is the x-coordinate of our center of mass. In the next video, we'll talk about finding the y-coordinate of this center of mass, and we'll finish this off.